In this lecture, we talk about Tate groups. So we start with M, a G module, and then we have a norm map, which is defined like this. So here this group G is finite. So this sum here actually makes sense. So we have the sum. Now in this sum, instead of G, you can write G prime or G prime G. It doesn't matter. It still goes through all the elements. So you have the change of variable. So there are two things we can notice. So you have G prime norm will be just this. So this G prime acts on the norm, doesn't produce anything because you're still permuting through all the elements here of the group. Or you can take norm G prime M, then you are just doing change of variable here. So this is an important equality we have. So for these Tate groups, the only thing we need to do is the careful study of this norm map. So that is it. So you just do a careful study of this norm map and the Tate groups just drop out. So let us see the first observation. So instead of G prime, if you just write G here and transfer this to this side, then you can rewrite this as like this. So instead of G prime, you just write G. So you have norm G minus 1 M is 0. So recall that in one of the first lectures on the playlist, we had talked about this augmentation ideal. So we said this augmentation ideal is generated by this G minus 1. So this is how the augmentation ideal looks like. So this will obviously lie in the kernel because this is precisely how the augmentation map looks like. So this is our first observation. And you notice that the G prime acts on it, nothing happens. So the image of norm is within this M superscript G. So those elements which are fixed by G, the G acts on them and nothing changes. So the norm map induces a map from M subscript G to M superscript G. So this is coming right here, and this we have talked about in previous lecture. This is just defined as M modulo this, precisely here. So we have this map. So this is the only thing which we need to notice, or probably the most important thing. So this was the first thing, and this is what is leading us to this thing. So the norm map from here, you can restrict it to right here. And this is the norm map which we are going to consider. So once you have this norm map, you can talk about its kernel and co-kernel. So co-kernel is just our standard co-kernel, this mg modulo this. For kernel, we're going to talk about kernel of norm of G. So you can relate it to this kernel of norm of G, but now we have this M subscript G here instead of this M. So you have to modulo out with this IgM here. So again, notice that this M and this M are the same, and you have to modulo out with this IgM because this is here. So this is what you get. So this is our co-kernel and this is our kernel. And you have this nice short exact sequence. And this is going to be useful later on. So nothing has been done. You descended from here to here and you constructed this. And that is all the technology we need, going from here to here and talking about kernel and co-kernel. And now everything would be obvious. Now we define the ith Tate group. So the ith Tate group is defined as this superscript I. So this is just T for Tate. So you have this superscript I for I greater than 0. So for I greater than 0, you have our standard cohomology groups. For I equals to 0, you have the co-kernel. So this co-kernel right here, this is going right here, and this kernel right here, this is going right here. So for I equals to -1. So 0 and -1, they are coming from here and here. And for less than -1, you have this, which is the homology groups. So these are the homology groups. Only thing is you are just changing the indices here. So just putting extra -1. This will be clear once we start drawing it properly. Before we go further, if M is an induced G module, then all these are 0 for all integers. So obviously we are starting with G of finite, so this induced and co-induced are going to be the same. So now let us see that how such a definition would have arisen. So we have given this definition, so we want to see how this would have arisen, and I want to see this in action. So we are given a short exact sequence of G modules like this. Then you can form two long exact sequence. One long exact sequence is corresponding to the homology. So this is the sequence corresponding to homology. So you're going from C to this A, B, C, 0, ending here. And the second sequence you can form is cohomology. You start from the 0th cohomology group, so A, B, C, then the first cohomology group, and so on. So you have these two sequences. So once you make these two sequences, you can form the maps here. So recall that the homology groups, this look like this. So this is A subscript G, and this map here is A superscript G. So this here is A superscript G. Similarly here, this is homology, so this is this group, this is this group, this is this group, this is this group. So exactly like this. So now you can use the snake lemma. So there is an entire playlist on snake lemma and how to prove it. So very important playlist to see. So now you can have a snake lemma. Again, this is just the norm map. So the norm map here. So again, you have a norm map here. You have the norm map here. So what you will do is we will have the kernel here and the co-kernel here. So kernel will look something like this, and the co-kernel will look something like this. So you will have kernel here, a kernel of norm here, kernel here, and then you have co-kernel here, co-kernel here, co-kernel here. So kernel and co-kernel are exactly like this. So kernel will look like this. So instead of M, you have A here. Instead of this M, you have B here. Instead of M, you have C here. Similarly, this co-kernel thing will come here, and you replace M with A, B, or C. So these arrows will now become like this, going to kernel, and this will go right here, and this map will continue. So this is precisely what we have done here. So this kernel is precisely what is here for -1, and this kernel again for -1, because this kernel again for -1. So -1 is here, and then 0th are here. So this is the co-kernel map. This is the co-ker. As you can see, this is the co-kernel. Again, co-kernel here, and the co-kernel is here. So let us write this more formally. So again, we have this homology sequence here, and this is our cohomology sequence, and then this group we copy as such right here. So that is how you get this -2 here. So this 1 becomes -2, so it's shifting an index. This you just copy right here. So cohomology groups remain the same. So notice how this homology group, which was 1, became -2 here, and this, which was first cohomology group, remained the same. So this is what one needs to remember. So obviously here you are going to have H1, but now the module, instead of C, you will have B, and therefore you will write H -2 Tate here. Instead of C, you will have B, and so on will go on. So you just have to change this 1 to -2, this 1 more here. So this is what is happening here. Cohomology groups we are not touching, and we said before this is just the kernel, and the kernel, and these are for I equals to -1. So notice the kernels here. We had written kernel, this kernel, and this kernel is precisely corresponding to this kernel here, and that is what we are writing as -1, -1, -1. And the co-kernel is here corresponding to 0, so that is what you have 0, 0, 0, our co-kernel maps. So we had written co-kernels here for the norm map, and that is what we have. And this was our snake thingy, and that is what our green arrow is. And so you have gotten a Tate group here. So this is what the Tate group is, or you can call it Tate cohomology groups, because you're putting I at the top here, And as I said before, this just comes from a careful consideration of just the norm map. So carefully looking at the norm map uh, helps us glue the homology sequence with cohomology sequence to get Tate groups.